The next topic in probability and statistics that I want to discuss is permutations and combinations. And here we'll first look at basic definitions and then do some examples. Now, the section on permutations and combinations from the reference handbook is shown here. And the definitions are that, first of all, a permutation is any ordered subset of size or length r of a set of n distinct objects. And the number of different permutations is given by this equation, which we write as Pnr is equal to n factorial divided by n minus r factorial. And this is sometimes written as NPR, like this. On the other hand, a combination is an unordered subset of size or length r of a set of n distinct objects. And the number of different possible combinations is given by C n of r, which is the number of permutations divided by r factorial, or n factorial divided by r factorial n minus r factorial. And this is sometimes written as either NCR or NR in this fashion here. To show this, let's do an example. Let's suppose that we have 8 surveyors who are eligible for promotion. However, there are only 3 available promotion slots. How many different combinations of promoted surveyors are possible? Which of these alternatives? So let's go through this logically, and let's suppose that the 8 surveyors are labeled A, B, C, D, E, F, G, H. So we can start thinking of the number of ways that we can arrange any 3 of those in groups. So there would be, for example, ABC would be a combination, ABD, etc., all the way up to the last one, which is FGH. And overall, the number of combinations is given by a basic expression here. Cn of r is n factorial divided by r factorial n minus r factorial. So in this case, we have n, the number of people is 8, and we're rearranging those into groups of 3, so r is equal to 3, so that's equal to 8 factorial divided by 3 factorial times 5 factorial, which is, writing it out in all its detail, equal to that, which is equal to 56. So the answer is C. There are 56 possible combinations for promotion. Now, to see how this arises, let's do a simpler case where we can count up all the individual possibilities. What if there were only 3 surveyors and there were 2 possible slots, or 2 possible ways to arrange them? Then, in that case, our 3 surveyors are labeled A, B, C, and you see there are only 3 different combinations of those that we can make. Either AB, AC, or BC. So the answer is going to be 3. Now, note that BA is not a separate combination, because in this case it's a combination, the order doesn't matter. So AB and BA are not separate combinations, and there are only, in this case, 3 available, as here. Well, does the equation agree with that? So in this case, again, the same general equation applies here for C and R, but now n is equal to 3 and r is equal to 2, so that is equal to the expression here, which, expanding it out, is equal to that, and the answer is 3. So indeed, we can see that this is correct. What about, though, if we wanted to get the number of permutations? So now the number of permutations, the order does matter. So AB and BA are now separate, different permutations, and there are more possibilities available. So in this case, you see, we're going to have 6 possible permutations, and those are them right there. Does that agree with our equation? Well, now we have P of 3, 2 is 3 factorial divided by 3 minus 2 factorial is equal to that, which is equal to 6. So indeed, again, that does work. This problem concerns a combination lock like this, and the combination lock consists of 4 numbers or digits which range from 0 to 9. They're integer numbers. And we're given that the numbers in the combination must increase from first to last, and each number can be used only once. How many different possible combinations are there out of these 4 alternatives? So again, let's think about this logically. These are the 10 digits, 0, 1, 2, 3, up to 9. So if we start thinking of the possible combinations, they look like this. The first one is 0, 1, 2, 3, 0, 1, 2, 4, etc., up to the last one, which is going to be 6, 7, 8, 9. And in this case then, 0, 1, 3, 2 is not a possible combination because it doesn't increase in order. And 0, 1, 2, 2, for example, is also not a possible combination because that uses the digit 2 twice, and we can only use them once. So again, this is a combination problem. The answer is Cn of r is usual equation. And in this case, we have n is equal to 10. There are 10 digits. And r is equal to 4. There are 4 combinations in the final set. So expanding that out, we have this number, and computing that, the answer is 210. So the answer is B. What if we had different rules, though, for this? Let's, for example, say that the order doesn't matter, but again, the numbers can be used only once. So now the number of possibilities is much more. Now we can have 0, 1, 2, 3, and now we can include 0, 1, 3, 2 in that because we're using the numbers only once, but now the order doesn't matter. So we can rearrange the order of those numbers, and we have more possible permutations. So in this case, this is given by our permutation equation. Pn of r is n factorial over n minus r factorial. Substituting in the numbers, then that's equal to 10 factorial divided by 10 minus 4 factorial, or 6 factorial, which is equal to this. And computing out the number, the answer is that there are 5,040 possible combinations according to those rules. The normal way of setting a combination lock, of course, would be that the order doesn't matter and the numbers can be used more than once. So that gives us many more possibilities, starting from 0000 up to 001, etc., all the way up to the last one, which is 9,999. And you can see then that obviously the total number of combinations in that case is equal to 10,000. And this concludes our discussion of permutations and combinations.